Okay, so let's graph some rational functions. So what is a rational function? Well, a rational number is a fraction. A rational function is a fraction where you have a polynomial on the top and a polynomial on the bottom. So the numerator is a polynomial, the denominator is a polynomial. That's a rational function. So here's the simplest, most basic example of a rational function, 1 over x. Let's graph this function. So if I ask you to find the initial value, or f of 0, you would have 1 over 0. You guys know that's undefined. So f of 0 is undefined. You cannot have a 0 on the bottom of a fraction, so that's very important. All right, let's plug in a 1 to this function. So f of 1, well, 1 over 1 is 1, so we can plot that point. Let's plug in a 2. So if I put a 2 in, f of 2 would be 1/2, or right here. If I plugged in 3, f of 3 would be 1/3. 1/3 is less than 1/2, so that would be about here. If I plugged in 4, I would get 1/4. 1/4 is less than 1/3, so that would be even closer to the x-axis, so maybe there. If I plugged in 5, I would get 1/5. 1/5 is even less than 1/4, so it's even closer to the x-axis. Okay, so say I plugged in maybe a 10 way out here. So if I plugged in a 10, I would get 1/10, which would be very close to the x-axis. If I plugged in 1,000 for x, way out here somewhere, I would get 1,000, would be really, really, really close to the x-axis. So what's happening is this function, the output of the function is getting smaller and smaller and smaller. It's getting closer and closer and closer to the x-axis forever. So what I'm going to do is put a dotted line out this way, and this value keeps getting closer and closer and closer to that dotted line. But will it ever touch the x-axis? No, there's no way to get a 0 out of it. No matter how big my x is, if I put 1,000,000 in for x, I would get 1 over 1,000,000, which would be a tiny little number, but it wouldn't be 0. I can plug in a number as big as I want for x, and I can make the output be as small as I want, but I can never get it to 0. Okay, so this graph keeps getting closer and closer to the x-axis. This dotted horizontal line is called an asymptote. And in fact, specifically, it's called a horizontal asymptote. Asymptote. That's a horizontal asymptote. And what that means is that the graph keeps getting closer and closer to that horizontal asymptote, but never touches it. All right, so we couldn't plug in 0, but what if we plugged in -1? Well, 1 over -1 would be -1. I'll get that. If I plugged in -2 for x, I would get -1/2, which would be about here. If I plugged in -3, I would get -1/3, which would be here. And then I would get -1/4 when I plug in -4, -1/5, and so on. And you can see what's happening. The graph is getting closer and closer to this dotted line. Closer and closer to that horizontal asymptote, but it never touches it. All right, so we've graphed all of these points except the numbers between -1 and 1. So let's think about what happens when we plot those points. Okay, so let's plug in maybe 1/2. Okay, so there's 1/2. So what is f of 1/2? Well, that would be 1 over 1/2. When you divide by a fraction, you multiply by the reciprocal, so that would be 1 times 2 over 1, which would be 2. Okay, so if I plug 1/2 into the function, it spits out a 2. What if I plugged in 1/3? 1/3 is less than 1/2, so 1/3 would be about here. If I plugged in 1/3, I would get a 3. If I plugged in 1/4, which is less than 1/3, I would get a 4. Should be about here. If I plugged in a 1/5, which is even smaller, I would get a 5. And so on. Okay, I could plug in 1/1,000,000 and I would get 1,000,000. So what's happening is this graph is going that, and it's getting closer and closer to the y-axis, but it never actually touches the y-axis. So I'm going to put a dotted line up this way, and we have a vertical asymptote. So that is a vertical asymptote. So I can plug in numbers for x as close to 0 as I want, really, really tiny x values. The smaller I make my x value, the bigger the output of my function. What about these numbers? So if I plug in maybe -1/2, well then I would get -2. It's here. If I plugged in -1/3, I would get -3. Plug in -1/4, I would get -4. And you can see what's happening. The graph is headed down that way, and you have a vertical asymptote there. All right, so let's ask some questions about this graph or this function. So this says as x approaches infinity, f of x approaches what? Okay, so this little arrow I'm going to use as an abbreviation for the word approaches. So as x approaches infinity, f of x approaches what? Okay, so what this means, if we say x approaches infinity, that means x keeps getting bigger and bigger and bigger forever. So as my x gets bigger and bigger and bigger forever, what happens to the f of x value? Well, as x gets bigger and bigger and bigger out this way forever, my f of x value gets smaller and smaller and smaller. Gets closer and closer and closer to 0. So for instance, if I plug in 10 for x, my f of x value is 1/10. If I plug in 100 for x, way on out here, then my f of x value would be 1/100, really close to 0. If I plugged in 1,000 for x, way on out here somewhere, way out this way, then I would get 1,000th for my f of x value, which would be really, really close to 0. So as x approaches infinity, f of x approaches 0. Keeps getting closer and closer to 0. All right. As x approaches negative infinity, what happens to my f of x value? Okay, so as x gets smaller and smaller and smaller out this way forever, more and more and more negative in this direction, out this way, what happens to my f of x value? Well, it gets closer and closer and closer to 0. Right. As x approaches 0 from the right or from above, so this little plus sign up here means from the right or from above. So numbers just a little bit bigger than 0, 0.1, 0.01, 0.001. So as x gets closer and closer to 0 from the right, what happens to my f of x value? So as the x gets closer and closer to 0 from above or from the right, so these numbers right in here, what happens to my f of x value? Well, it keeps getting bigger and bigger and bigger forever. So f of x goes to infinity. Right. As x approaches 0 from below or from the left, so this little negative sign means from below. So as x approaches 0 from below, so we're talking about these numbers, 1/2, 1/3, 1/4, 1/5, 1/10, 100th, 1,000, excuse me, -1/2, -1/3, -1/4, -1/5, -1/10, -100. So these little numbers in here, what happens to my f of x value? Well, the closer my x gets to 0 from the left, the smaller my f of x value gets. So it goes to negative infinity. All right, so let's graph this function, g of x equals 1 over x minus 3. Okay, so first of all, notice that we cannot plug 3 into this function. If we plug in 3, we would get a 0 in the denominator, which is bad. So g of x is undefined for x equals 3. So we'll make note of that. All right, let's plug in maybe a 4. Okay, so if I put a 4 in, 4 minus 3 is 1. 1 over 1 is 1. So I would have that point. Let's plug in a 5. If I plug in a 5, I would get 5 minus 3 is 2. I would get 1/2, which would be here. If I plug in a 6, 6 minus 3 is 3, and I'll get 1/3. This would be a little bit less than 1/2. If I plug in maybe a 7, 7 minus 3 is 4, I would get 1/4. And we have that familiar pattern again, where the graph keeps getting closer and closer to the x-axis, but never quite touches it. So we have a horizontal asymptote going out this way. Let's plug in a 2. So if I put in a 2, 2 minus 3 is negative 1. 1 over negative 1 would be negative 1. If I plugged in a 1, 1 minus 3 is negative 2. I would get negative 1/2. If I plug in 0, 0 minus 3 is negative 3, so I'll get negative 1/3. Put in a negative 1, and I would get negative 1/4, and so on, and we get that familiar pattern again, where the graph keeps getting closer and closer and closer to the x-axis, but never touches it. Okay, let's put in, say, 3.5. Okay, so if I put in 3.5, 3.5 minus 3 would be 0.5, or 1/2. You would have 1 over 1/2, which would be 2. So we get that point. And you can see that familiar pattern again. And we go right up that asymptote. So for instance, if I plugged in 3.1 right here, 3.1 minus 3 would be 0.1 or 1/10. Let's write that out. Let's do g of 3.1. Okay, so that's 1 over 3.1 minus 3, which is 1 over 0.1. 0.1 is 1/10, so we have 1 over 1/10, which would be 10. So if I plug in 3.1, I would get a 10 right here, and you can see what's happening. Okay, same thing here. If I plugged in 2.9, let's say, 2.9 minus 3 is negative 0.1. So you would end up with negative 10 somewhere down here, and you can see what's happening. The graph is going down that asymptote. All right, so now on the original 1 over x, notice the vertical asymptote was on the y-axis at x equals 0. Now the vertical asymptote is at x equals 3. That should be expected, because this is just a transformation of this function. Notice that this is, so g of x is 1 over x minus 3. That's just f of x minus 3. All right, if I put x minus 3 into the f function, I'll get 1 over x minus 3. You guys know from our discussions of transformations of functions, if I do f of this minus 3 inside of the parentheses, we'll shift the original function 3 to the right, and that's exactly what happened there. All right, so let's graph this function, g of x. Notice, first of all, that the function is undefined when x is equal to negative 3. We can't plug a negative 3 in. So let's note that spot. All right, then let's plot some points. All right, so if I plug in, say, a negative 2. So negative 2 plus 3 would be 1. Negative 2 over 1 is negative 2. Plus 4 would be 2. So we have that point. If I plugged in a negative 1 plus 3 is 2. Negative 2 divided by 2 is negative 1. Plus 4 is 3. Let's plug in a 0. So I would have negative 2/3 plus 4. So 4 minus 2/3 would be 3 1/3. So somewhere in that area. Let's plug in a 1. So if I put in a 1, 1 plus 3 is 4. Negative 2 over 4 is negative 1/2 plus 4. 4 minus 1/2 is 3.5. So I plug in a 1 and I get a 1, 2, 3. I think I plotted that point in the wrong spot. Let me try that again. Let's go back to 0. All right, so if I put in a 0, I get negative 2/3. 4 minus 2/3 is 3 1/3. 3, 1, 2, 3. 3 1/3 is here. Try that again. That looks better. All right, put in a 1. 1 plus 3 is 4. Negative 2 over 4 is negative 1/2. 4 minus 1/2 is 3.5. So we would get a number about here. Okay, plug in a 2, let's say. 2 plus 3 is 5. Negative 2/5. 4 minus 2/5 is 3 3/5. So that would be about here. And so on. All right, let's plug in a negative 4. So negative 4 plus 3 is negative 1. Negative 2 over negative 1 is 2. 2 plus 4 is 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that is there. All right, let's plug in a negative 5. So if I put negative 5 in here, negative 5 plus 3 is negative 2. Negative 2 divided by negative 2 is 1. 1 plus 4 is 5. All right, so I plug in negative 5, and I got a 5. 1, 2, 3, 4, 5. So that is here. Okay, let's plug in negative 6. So negative 6 plus 3 is negative 3. Negative 2 divided by negative 3 is 2/3. 2/3 plus 4 is 4 2/3. So if I plug in negative 6, I get 1, 2, 3, 4 2/3, which would be about here. Let's plug in a negative 7. So if I put in negative 7 plus 3 is negative 4. Negative 2 divided by negative 4 is positive 1/2. So I get 4 1/2. 1, 2, 3, 4, 1/2. So that would be about here. I'm not drawing this very straight. Let me move that one up a little. There we go. All right. So what's going on here? So this, here we have this. All right, so what's happening? As I plug in numbers farther out this way, this graph keeps getting closer and closer to 4. So what we have is a horizontal asymptote here at 4. And notice the same thing in this direction. Horizontal asymptote. Maybe, like on the other, maybe we have a vertical asymptote here at negative 3. Let's see if that's really the case. So let's plug in, say, negative 2.5 right here. So put in negative 2.5. So negative 2.5 plus 3 would be 1/2. Negative 2 over 1/2 divided Divide by the reciprocal, that would give you -4. Plus 4 would be 0. So I would get a 0 if I plug that in. And sure enough, you can see that we're going right down that asymptote. Let's plug in a -3.5. Okay, so if I put in -3.5 plus 3, that gives me -1/2. So I have -2 over -1/2, which would be a +4. Plus 4 is 8. So 1, 2, 3, 4, 5, 6, 7, 8. One more. So up here, and sure enough, we're going right up that asymptote. All right. Is that what we expect would have happened? So let's think about this. The x plus 3 down here shifted this graph 3 to the left. So the vertical asymptote was on the y-axis. Now we moved it 3 to the left. That makes sense. This plus 4 out here shifted this graph up 4 units. So the horizontal axis was on the x-axis. Now it's been moved up 4. So it's there. And this -2 on the top, well, that's just -2 times this. So multiplying by a negative number should flip this graph upside down. And you can see that happen. This part got flipped across the x-axis so that it looks like this, and it does. This part gets flipped across the x-axis so it should look like this, and it does. So specifically, we could say that this is -2 times f of x plus 3 plus 4. All right, so if I do f of x plus 3, I put x plus 3 in here, so I have 1 over x plus 3 times -2, so that's -2 over x plus 3 plus 4. And as you guys remember from our studies of transformations, the plus 3 shifts this graph left 3, multiplies all the y values by -2, so it flips it upside down, and it shifts the graph up 4. So we get exactly what we would have expected. All right, so it's of interest. So it's of interest to rewrite this function in a different form. So let's do that. To add this 4, let's get a common denominator. Okay, so I can make this be 4 times x plus 3 over x plus 3. So all I did was get a common denominator here. Multiply 4 over 1 at the top by x plus 3, at the bottom by x plus 3. So now I have a common denominator. So I have -2 plus, and I'll go ahead and distribute the 4. So that'll be 4x plus 12 all over x plus 3. And I'm out of room there, so let's come way up here. If I simplify, 12 minus 2 is 10. So I have 4x plus 10 all over x plus 3. So I could write g of x in that form. Okay, notice that the numerator is a linear equation or linear expression. The denominator is a linear expression. They both have degree 1. Right? So this is degree 1, this is degree 1. There's an understood 1 right here. So I can look at these numbers in front of the x's. That's 4 over 1. Where is my horizontal asymptote? It's at 4. So that's kind of an interesting observation. All right, so let's see if we can graph this function. So the first thing we could do is maybe factor this bottom. So that's a difference of squares. I could factor it into 2 conjugates, x plus 3 and x minus 3. So the first thing to notice is that the function is undefined at -3 and +3. Okay, so let's make note of those points. 3 and -3. It's going to be undefined there. So maybe we have those vertical asymptotes at that spot. right, those x values again. So let's plot some points. Let's do, let's work right around the 3 here. So let's try f of 2. Okay, so if I plug 2 in for x, 2 squared is 4. 4 minus 9 is -5, so I'll get -1/5. Let's do f of 1. 1 squared is 1. 1 minus 9 is -8, so I get -1/8. Let's do f of 0. That would be -1/9. Let's do f of -1. So -1 squared is 1. So I'm back to -1/8. F of -2. That would be 4. Minus 9 is -5, so I get -1/5. Okay, so let's plot those points. So f of 0 is, there's -1. So -1/9 is here. F of 1 is -1/8. So that would be just a little bit farther down. F of 2 is -1/5. A little bit farther. I don't quite have those. Let me fix that up a little. 1/9 would be really close in there. And 1/8 would be almost as close. 1/5, very close. But notice it's symmetric on the other side, so I got -1/8, -1/5, so on. So it looks like that. All right, let's plot 4. Let's find f of 4. All right, if I put a 4 in, 4 squared is 16. 16 minus 9 is 7. So I would get a 1/7. So no, it's positive. 1/7 would be about here. Area. If I did f of -4, we're going to get the same number because -4 squared is 16. 16 minus 7. And I'll get the 1/7 again. Okay. Let's try just a couple more, see if we can figure out what's going on. All right, so let's do f of 5 this time. 5 squared is 25. 25 minus 9 is 16. And of course, f of -5 would also be 16. No, I'm sorry, it would be 1/16. 1/16 and 1/16. All right, so let's see if we can plot those. See, that was 1/7, so this would be even smaller. And this would be even smaller. Okay, so it looks like we need to plot some points. Just to tell what's going on, we need to plot points between 2 and 3 and between 3 and 4. So things like 2.5. So let's do f of 2.5. And let's do f of 3.5. And see if we can figure out what's going on. All right, so I cheated a little bit and used a calculator to get these numbers. So I plugged in 2.5, which is right here, and I got -4/11, which would be somewhere in this area. And I plugged in 3.5 and I got 4/13, which would be somewhere in this area. All right, but so I wanted to get really close to 3, so I plugged in 2.99. So really, really close to 3. And my calculator told me that that came out to be approximately -16.7. So if I plug in a number really, really close to 3, I get a number way down here. And if I plug in a number just barely bigger than 3, I got 16.6, so a number way up here. So what we have here is a vertical asymptote here. And this goes like that. And it will follow right out the x-axis here. We'll have a horizontal asymptote that way. So we could plug in really big numbers like 100. If I plug in 100 to this, 100 squared is a really big number. Minus 9 is still a really big number, and you have 1 over a really big number, which would be a really small number. So something really close to 0 out that way. And then, so this is, we can see it's symmetrical. So this same thing is going to happen here. We will be going up this asymptote, and we will be going right out this asymptote. And this point will be symmetrical over here, and you can see we have this, and that is very bad drawing. This should not be flat, it curves a little bit. It's pretty hard to draw. There we go. So it looks something like that. So we have two vertical asymptotes. The graph goes down each one of those here. It goes up the asymptote here and here, and it goes out the asymptotes on the x-axis. All right, so a couple of things to notice here. First of all, the function was undefined at 3 and -3, and we had vertical asymptotes at those points. Notice also that the degree of the denominator is 2. The degree of the numerator is 0. You have an understood x to the 0 up here. Remember, anything to the 0 power is just 1, so that's just 1. So the degree of the top is 0. The degree of the bottom is 2. So the degree of the denominator is less than the degree of the numerator. And notice that our horizontal axis, or our horizontal asymptote, was on the x-axis. Okay, so the degree of the numerator was less than the degree of the, let me try that one more time. The degree of the denominator is greater than the degree of the numerator. And my horizontal asymptote was on the x-axis. All right, let's see if we can graph this function. So I don't want to just start plotting points on this because this looks fairly nasty. It looks a little complicated to just plot points. But notice that we can factor the bottom, or the new denominator. Okay, so if I factor the denominator, I can factor it into x plus 4 and x minus 3. So right off the bat, we should notice that this function is undefined when x is -4 or x is equal to 3. Okay, so let's start making a graph. X, 1, 2, 3. So it's undefined at 3, and it's also undefined at 2, 3, 4, at -4. Okay, because either -4 or 3, if I plugged either one of those into this function, it would be undefined. I would get a 0 in the denominator. All right. Notice that I can cancel the x minus 3's. So f of x would be equal to 1 over x plus 4, assuming x is not equal to 3. Okay, so as long as x is not 3, these two are the same. This would be equal to 1 over x plus 4, just by crossing out the x minus 3's. We know exactly how to graph this. Okay, this is 1 over x shifted to the left 4 units. It should be undefined here, so we know that we're going to have a vertical asymptote here. And we know exactly what the graph looks like. It's going to do this and this because all we did is shift 1 over x over 4 units. So this is 1, then -3 should be there. And -5 should give me that number. Let's check and make sure that really works. So if I plug -3 into this function, I should get a 1 out of it. So if I put -3 here, -3 minus 3 is -6. If I put a -3 here, that would be 9 plus 3 is -3, that's 9. Minus 3 is 6. 6 minus 12 is -6. And I get a 1. If I put in a -5, -5 minus 3 is -8. 25 minus 5 is 20. 20 minus 12 is 8, and I get -1. So exactly what I should get. And we know that the graph looks like this, and it goes right out the x-axis that way. And it does the same thing here. Just like that. Okay. But if I graph this equation, or this function, I would not have a vertical asymptote at 3. There's nothing to do with the 3 here. But this equation should be undefined when x is equal to 3. So what's going on here? So notice that this is really important. These two expressions are equal, only assuming that x is not equal to 3. Okay, so this graph looks exactly like this graph everywhere except this point. Okay, so right here, I've graphed this. So this graph is this, which looks like this everywhere except when x is 3. So what actually happens here is there's going to be a hole in the graph. So I'm going to make an open circle there. Right here. There's going to be a hole in the graph at that point. Okay. So let's figure out what the y value is for this hole. So if I plug 3 into the original function, it's undefined. There's going to be a hole. But if I plug 3 into this, I get 1 over 7, which is okay. So we know this y value right here is 1/7. So this hole is at the point 3, 1/7. So there's a hole in my graph right at this single point. There's no vertical asymptote here. There's just a hole in the graph. All right, so let's ask some questions about this function now. All right, so as x approaches negative infinity, so as my x gets smaller and smaller and smaller forever out this direction, what does my f of x value get closer to? Well, as I plug in these smaller and smaller x's, my f of x value keeps getting closer and closer and closer to 0. As x goes to positive infinity, so as far out this way as we can go on the x-axis, my f of x value will keep getting closer and closer and closer to 0. As x approaches -4 from the left, so as we come in here, closer and closer, my f of x value will go to negative infinity. As x approaches -4 from the right, so from this direction, my f of x value goes to positive infinity. Right, as x approaches 3 from the left, what happens to my f of x value? So as I come toward 3 from the left, so from this side, I plug in these x values right here, closer and closer to 3, and my function value will keep getting closer and closer and closer to 1/7. Okay. As x approaches 3 from the right, so now I'm going to plug in these x values. my function value again gets closer and closer and closer to 1/7. But remember, I can't plug 3 in for x. If I plug 3 in for x, my function is undefined at that point. So I need that hole in the graph. But I can get as close as I want to that point. I just can't touch it. All right, notice again that the degree of the denominator is bigger than the degree of the numerator. The degree is 2, the degree is 1. And notice again that my horizontal asymptote is the x-axis. We're looking at it down here. The degree is 1, the degree is 0. The degree of the denominator is bigger than the degree of the numerator. And my horizontal asymptote is on the x-axis. All right, so let's graph one final example here. Again, I don't want to just plot points on this because it's a pretty big mess. But notice that this function is undefined when x is equal to 4. So it's going to be undefined at 4. All right, what to do? I don't want to just plot points, but notice that I can factor the numerator. So I can do 3x, that'll give me the 3x squared. I can do 4 and 1. That and get it factored, so double check that. That's 3x squared minus 12x plus 1 is minus 11x minus 4. Now, as long as x is not 4, I can cancel those two terms out. So this is the same as 3x plus 1 as long as, or assuming, x is not equal to 4. Hey, I know how to graph this. That's just a linear equation. 3x plus 1, the y-intercept is 1, the slope is 3. So my y-intercept is at 1, my slope is 3, so I go up 3 over 1, up 3 over 1, and so on. And I just get this straight line here. I'm not even going to mark that off. It just looks like this. But be very careful. F of x is equal to this linear equation only if x is not equal to 4. Okay, because remember, if x is equal to 4, then f of x is undefined. Okay, so you can't plug 4 into f of x, it's undefined. I can plug 4 into this equation, but not into this one. So this is equal to this only if x is not equal to 4. Okay, but if I did plug 4 into this straight line, I would get 3 times 4 is 12 plus 1 is 13. So what that means is that there's a hole in my graph right here at 4. And that hole has the y value of 13. So this hole is at the point 4 and 13. All right, notice this. This time, the degree of the denominator is 1. The degree of the numerator is 2. So the degree of the denominator is less than the degree of the numerator. Let me re-say that in case I misspoke. The degree of the denominator is less than the degree of the numerator. And notice in this case now, there is no horizontal asymptote. All right, so let's summarize what we have, the examples we've seen so far. So say we've got a rational function. Okay, so a rational function is just a function where you have a polynomial on top and a polynomial on the bottom. Your numerator is a polynomial and your denominator is a polynomial. So this is just, all this mess out here is just the general form of a polynomial. All right, let's say that we have this function fully factored. So we factored it and we've canceled out all the common factors. Okay, so it's fully factored out. All the common factors have been canceled away. If you've done that, then with the polynomial or the rational function you're left with, you will always have a vertical asymptote at any of the zeros of the denominator. Okay, and we did several examples of that. We found the zeros of the denominator, and we had vertical asymptotes at that point. Before you cancel out all the common factors, your function will be undefined at all of the zeros, but on the ones you cancel away, you'll just have a hole in the graph there. It won't be a vertical asymptote. Okay, so before you cancel away the factors, if your original function is undefined at that point, you'll have a hole in the graph on the ones that you cancel away, on the factors that you cancel away. Okay, after you've canceled everything away, the remaining zeros of the denominator will have vertical asymptotes at that point. All right, and then next, if n is less than m, so if the degree of the numerator is less than the degree of the denominator, then there will be one horizontal asymptote along the x-axis, or at y equals 0. Okay. If the n is equal to the m, so if the degrees are the same, then you'll have a horizontal asymptote along the line y equals a sub n over b sub n, or the ratio of the leading coefficients. So you can just look at this fraction sitting in front, and that's where your horizontal asymptote will be. If n is greater than m, so the degree of the numerator is bigger than the degree of the denominator, then you will have no horizontal asymptotes for that function.